This is a video about the mole, a brief introduction to the mole, and some simple unit conversions using the mole. I'd like to emphasize, first of all, that the mole is actually a much more simple concept than a lot of people think. It is simply a counting number. Anything that can be counted, from marbles to toes to pieces of paper, atoms, molecules, can be described as part of a mole. So just like we say that a dozen of anything that can be counted is 12, a mole happens to be 6.022 times 10 to the 23rd of those items. And the reason that's so ridiculously huge is because atoms and molecules are so incredibly small that it takes this many of them to have enough to just like hold a little bit in your hand or measure it and do anything with it. So as I said, you can have a mole of anything, just like you can have a dozen of anything. But it doesn't make a lot of sense, because a mole of anything other than something that's almost infinitesimally small, like an atom or molecule, would be a ridiculous quantity. Like if you had a mole of marbles, for example, they would completely cover the earth and extend up a ways. So it really doesn't make sense to refer to a mole of anything other than chemicals. So to give you an idea, a mole of water molecules, so 6.02 times 10 to the 23rd water molecules, is about 1 tablespoon of water. And just to remind you, is the mole, this number, is referred to as Avogadro's number. All right, so again, in chemistry, a mole can be used to describe the quantity of any type of particle. So commonly used particles in chemistry are atoms, molecules, formula units, which is the name that we call, instead of molecules for ionic compound, we call them formula units. Ions are countable, and you could have a mole of them. Chemists are, the unit that's most useful to chemists is mass, because if you've taken chemistry lab, you know that that's pretty much how you start, determining quantities, is you weigh them out, or you take the mass of them on a balance. And so it's important to be able to convert from mass to numbers of atoms. You need something like numbers of atoms when you start chemical reactions and do stoichiometry. So this conversion between units is pretty important. I think that if somebody said, how many eggs are in 5 dozen eggs, that you would just intuitively know that since there are 12 eggs in 1 dozen, that there must be 5 times that many. Oh, my pen's not working very well. 5 times 12 eggs in a dozen, or 60 in 5 dozen. That's really, it's that simple for mole conversions too, okay? So again, if 1 mole is 6.02 times 10 to the 23rd atoms or molecules, and I asked you how many atoms or molecules were in 5 moles, it's the same type of process, okay? All right, so before we start doing mole conversions, I just want to emphasize that every unit conversion or every dimensional analysis needs a conversion factor. And that is simply a ratio of equivalency where the quantity described in the numerator equals the quantity described in the denominator. They just have different units, okay? And the conversion factor is what allows you to convert units. So here's a real simple one, converting from moles to atoms, okay? All right, so there's a process that is helpful to follow in doing any type of unit conversion, And even though it may be tempting to ignore this process or try to memorize steps, when they get more complicated, when we get into stoichiometry and chemical reactions, this process is going to be real valuable. So here goes. The question or the problem itself will always give you at least one given value, one quantity with units that's given to you. Always start your problem with that given quantity first, okay? And then if it's helpful, you can set up, some people call these railroad tracks, whatever, or grid. And the important thing is what comes next in the process is your conversion factor, okay? And so remember the last page, I said you can arrange a conversion factor, call it right side up, upside down, whatever. But the way you arrange it, whether you have atoms or on top or moles on top, is determined by the units of the given information. So since our units here are moles, that means that the units in the denominator of our conversion factor must match. And that is because algebraically we are going to cancel units on the diagonal. Remember, you're trying to switch units. That's the whole purpose. Okay, so another thing is sometimes students get mixed up, and rather than putting the number 1 in front of mole on a conversion factor, they might accidentally put Avogadro's number in front of mole or some bizarre number. So I tell my students, whenever they write mole as part of a conversion factor, just automatically put a 1 in front of it right away. Just get in the habit of doing that. Of course, then the units you're trying to get to, the units the problem is asking for, in this case atoms, goes on the top. And again, whatever units you have in the upper right of your calculation will be your ultimate units. And then it's just a simple multiplication division problem, okay? You have 2 times 6.02 times 10 to the 23rd, all divided by 1. All right, what if we went in the other direction? What if the given information was in atoms and the problem was asking us how many moles that was equal to? Again, start with your given information. Make sure you write your units down. Now, in this case, we're using the same conversion factor that we did on the last problem, but remember that the denominator units must match the units of the given information. So this time we have to have atoms in the denominator so that they cancel. All right? And what goes in front of atoms? Anytime you see atoms or molecules, put Avogadro's number, okay? So jot that down if you need to, program it, whatever. Anytime you see atoms or molecules, some type of particle, you're going to put Avogadro's number in front of it. All right, then again, the unit you're trying to get to go in the numerator. The problem's asking for moles. And again, anytime you write moles for part of a conversion factor, automatically put that number 1. Now be careful here with your calculator. This is another simple multiplication division. But whenever you're using scientific notation, particularly if you're dividing, it's important how you enter it in your calculator. So this should be 6.02 times 10 to the 23rd times 1 divided by 6.02 times 10 to the 23rd. I would encourage you to enter that in your calculator right now. The answer should be 1, okay? If you get something funky, like 1 times 10 to the 46, some crazy exponent, that means you are entering it into your calculator wrong. So there are a couple ways to battle that. If you can either put the entire scientific notation values in parentheses, which will protect you, or you can find an easier way to enter scientific notation. So if you have a double E button, sometimes it's just a single capital E. Sometimes it's exponent button, and sometimes it's 10 to the X button. But if you use any of those rather than the old-fashioned times 10 caret and then whatever your exponent is, this is not a good way. That's too many keystrokes, too much confusion for your calculator. And you always need parentheses with that. But if you were entering Avogadro's number using any of these, you'd put the coefficient, 6.02. The double E or the exponent, all of these keys stand for times 10 raised to the. So you don't have to put in any of this times button, 10, caret, nothing. Then all you do is you put in the exponent. That's it. If you use one of these, you don't need parentheses typically. A lot less keystrokes, less room for error. All right, so here's one for you to try on your own. So I would recommend go ahead and turn the video off and see if you can work it, and then turn it back on and check the answer with me. Alrighty, I'm going to start with the given information. Okay. 0.050 moles of iron. I'm going to go ahead and set up my railroad tracks. I know that I have to match units on the diagonal, so I know that moles of iron has to go down here, and I'm going to put a 1 in front of that mole. The units I'm trying to get to go on top. It's asking for iron atoms. And whenever I see atoms or molecules, some type of particle, I'm going to put Avogadro's number, 6.02 times 10 to the 23rd. And now it's simply a multiplication division problem. So it's 0.050 times 6.02 times 10 to the 23rd. And so the answer to that is 3.01 times 10 to the 22. And what are your units? Well, the moles cancel, and the units in the upper right are your final units, so that's atoms. Now, if significant figures are important to your instructor, then you want to pay attention to this. This particular problem asks you to report the answer to 2 sig figures. So I would report it as 3.0 times 10 to the 22nd atoms of iron. Alrighty, so that's going back and forth. Sorry about that, it was my dog. That's going back and forth between moles and atoms or moles and molecules. And now let's talk about how to go back and forth between moles and mass, which is simply grams typically. All right, so our conversion factor in this case is the molar mass, just what you get off the periodic table. So our conversion factor when we're talking about molecules or atoms is Avogadro's number. Our conversion factor when you see grams is molar mass. So molar mass, just to remind you, just get it off the periodic table. I'm not sure if you're aware of this little interesting tidbit, but when you look in the periodic table, the value, for example, that you see for carbon, 12.0, that gives you the mass for 1 carbon atom, and just by changing the units but keeping the same quantity also gives you the mass for 1 mole of carbon. So, and that's part of where Avogadro's number comes from. It's the conversion between grams and atomic mass units, and it allows us to use the number we see in the periodic table for mass for either atoms or moles. So, for example, 1 carbon atom has a mass of 12.0 atomic mass units. Atomic mass units were thought up just for the mass of atoms and molecules and stuff because the mass is so small. It doesn't make a lot of sense to use grams. It'd be a very, very small number. And, okay, so 1 mole of carbon atoms, 6.02 times 10 to the 23rd moles, or atoms of carbon, would weigh or have a mass of 12.0 grams. So that's kind of cool. So we're not going to be working in atomic mass units, at least I won't be. So the units will be using, or the conversion factor will be using as grams per mole. Alrighty, so since molar mass is going to be your conversion factor, you want to make sure you know how to interpret chemical formulas and calculate the molar mass. So I think it's pretty obvious there are 3 calcium in this formula. It's calcium phosphate. But hopefully you know how to read subscripts around parentheses. So this tells us that there are 2 phosphorus and there are 2 times 4 or 8 oxygen. So if there are two subscripts next to each other, inside and outside of parentheses, you want to multiply them. All right, so then get the molar masses for each of the atoms in the compound from the periodic table. There are 3 calcium. Each calcium has a mass of 40.078, 2 phosphorus, and 8 oxygen. Now, I think it's very important when you get the molar masses off the periodic table that you never round to like a whole number. I recommend carrying at least 2 digits to the right of the decimal for every molar mass. Otherwise, you risk artificially rounding too much and actually getting an inaccurate answer at the end. So again, when you get the molar mass, remember the units are grams per mole. And what that means when we use a conversion factor is 310.18 grams of this substance equals 1 mole of this substance. So as any conversion factor, you think of it as the numerator and denominator being equivalent quantities, just different units. Should be a 1 there. And how you arrange the conversion factor, right side up, upside down, whatever, is going to depend on what the units you're given are. So let's do a simple one. What if the given information was 3 moles of aluminum and asking how many grams of aluminum is that equal to? So let's go ahead and set up this problem like we always do. And that is, you are going to start with the given information, just 3 moles. Either just set it up like a multiplication, or you can set up your railroad tracks if you prefer. Here's your conversion factor. So again, you want units to match on the diagonal so that they cancel. So we have to have moles down here in the denominator, put a number 1 in front of it. And then on top are the units we're trying to get to. This problem is asking for grams. So we want grams, the molar mass of aluminum. And then again, it's just simple multiplication and division. And we see that it's 81 grams of aluminum. All right, here's one that's a little bit more complex. So for this one, I would recommend turning off the video again, trying to work it yourself, and then I will work it for you. All right, I'm going to start off by calculating the molar mass of acetylsalicylic acid. So we have 9 carbons. And so that means 9 times the molar mass of carbon, 12.01. And that is, if I do my mental math right, 108.09. And we have 8 hydrogen. So 8 times 1.01 is 8.08 grams per mole. And then we have 4 oxygen. Now, I noticed that students commonly round the molar mass of oxygen wrong. The molar mass in the periodic table is 15.999. You can either write down all the digits, or if you round it 2 digits to the right, don't forget the rounding rules, okay? Wherever you cut it off, you have to look at 1 digit to the right. And if that digit to the right is 5 or higher, you're going to round up. So the correct molar mass for oxygen rounded is 16.00. All right. So the molar mass of acetylsalicylic acid is 180.17 grams per mole. The problem said that we are starting with 5.82 moles of C9H8O4, and it wants to know how many grams that is. Match the units on the diagonal, it's moles, put the number 1 in front of mole, and on the top, now, what are we trying to get to? The problem's asking us for grams. Anytime you see grams, you go straight to the periodic table and get the molar mass. So if you don't get anything else out of this lecture, I want you to know that when you see grams, go to the periodic table and get molar mass. And when you see atoms or molecules, use Avogadro's number. Nothing else, get those straight. All right, so the molar mass we just calculated, it is 180.17. Okay, cancel our moles, and now it is a simple multiplication problem. And let me do that real quick. 5.82 times 180.17 is 1,000 and by round 49. And the units are grams. That's it. All right, so just to summarize, we have gone back and forth between moles and number of atoms, okay? Using Avogadro's number as a conversion factor. We've gone back and forth between mass or grams and moles using the molar mass. And so notice now that moles is in the middle of everything, okay? You need to remember that. Moles is in the center of all mole conversions or all conversions. And so if your problem does not give you moles as your starting information, the very first step will always be to convert to moles. Okay, let me say that again. If the problem itself, if the given information of the problem is not already moles, the first step of any calculation will be to determine how many moles. So what happens if you're asked to go from grams of a substance all the way to atoms or molecules? Oh, how do you do that? You cannot go directly between grams and atoms. Remember what I said? Everything must go through moles. Okay, so this is a two-step calculation. Each arrow here represents a calculation. So if you started with grams, you would first have to convert it to moles, do a calculation, and the second step, go from moles to atoms. You can probably tell here that this is a really common student error because I made this slide trying to think, how can I emphasize that they can't ever go directly from grams to atoms or molecules? So put that someplace where you'll remember it. All right, we're almost done. This is called a mole map. Some people find it useful and helpful, and others don't. We aren't going to talk about this branch of the mole map for another bit, so you can ignore it for now. I'm going to show you how to use this map in case it's useful to you. So again, moles is in the middle of everything. So let's say that you're given information as grams, and they're asking you to go to particles. So you follow the arrows in the direction you want to go. If we start at grams, we want to go this direction, right, towards particles. And so that means we're going to divide by the molar mass, and that'll give us moles. And then to get to particles, we're going to go this direction again, and that means following this map, we're going to multiply by Avogadro's number. Now, what if we were going the other direction? So what if you started with particles and wanted to get to grams? Okay, follow the arrows in the right direction. Go this way. So that means the first thing you're going to do is divide by Avogadro's number. And then again, follow the arrows in the direction you're going, which tells us the second step will be to multiply by molar mass. Now, a little trick I'm going to show you. Anytime you're starting with moles, anytime your starting unit is moles, and you're going to any other unit besides moles, okay, it will always be a multiplication. Okay, multiplication, get it? Yeah. Okay. Again, anytime you're starting information as units of moles and you're going to any other units, it is always going to be a multiplication. Okay, if you start with any unit other than moles, so grams, molecules, atoms, whatever, and you're going away from them, it'll always be a division problem. So again, if you're starting with atoms or molecules, it will always be a division problem. Alrighty. All right, so the two-step calculation. Hopefully I've made enough of a big deal to tell you you cannot go in a direct one-step calculation from grams to atoms or molecules, or atoms and molecules to grams. Everything goes through moles. Okay, so that's always your first step. So in this case, here's the given information, 35.4 grams. Just follow the process 2 times. Some people like to break it into 2 separate calculations. You can do that if you want. Some people like to get an answer in between after the first one and then set up a second separate calculation. That's fine if that's more comfortable. All right, so given information is in units of grams, which means I need grams in the denominator so that they cancel. Anytime you see grams, look at the periodic table and get the molar mass. Okay, in this case, copper. Everything has to go through moles first, okay? So I'm going to write moles up here, put a number 1 in front of it. And then, like I said, you can either do this calculation and write the first step answer here, or you can just keep on going. If you were to stop the calculation at this point, your units would be moles of copper. But the problem is asking for atoms of copper. So we have another calculation to do. But you're going to follow the same process. We have moles on top here now. So we need moles in the denominator here so that they cancel. Put a 1 in front of mole always. And the units they're asking for are atoms. Again, anytime you see atoms or molecules, use Avogadro's number in front of that. And so now it is simply multiplying and dividing. It is 35.4 times 1 times 6.02 times 10 to the 23rd, all divided by 63.5. So I would recommend putting all that in your calculator and make sure you're using your calculator right and that you get the correct answer. All right, last slide. Here's one for you to try. So the tip-off here is that if moles is not mentioned in the problem, see how they're saying they're asking for mass and they're giving molecules, there's no mention of mole, that means it's a 2-step process, okay? So however you need to remember that. So I recommend turning off the video again, seeing if you can work this by yourself. Alrighty, so I went ahead and calculated the molar mass for glucose. And now I'm going to go ahead and set up the problem. Here's the given information, 1.20 times 10 to the 24th molecules of glucose. All right, so that gives me the units I need in the denominator of my first conversion factor. So that'd be molecules. Whenever I see molecules or atom, I'm going to automatically write Avogadro's number in next to it. All right, everything must go through moles. Okay, if this unit, if the initial units aren't moles itself, that's always the first step. So 1 mole on top. All right, if we were to stop now, our units would be moles. The problem is asking us for grams. Okay, so we have to do another calculation. Same process, match units on the diagonal. So we need moles down here. I'm going to put a 1 in front of it. The units we're trying to get to are grams, so that goes on top. And anytime I have grams, I'm going to look on the periodic table and use the molar mass, which I already found up here. So 180.18 grams per mole. And now it's multiplication division. So you have 1.20 times 10 to the 24th times 1 times 180.18, all divided by 6.02 times 10 to the 23rd. I would please punch this into your calculator if you haven't already, because again, when you have scientific notation, particularly when you're dividing by it, it's very easy to enter it incorrectly. And the answer is 359. What are our units? The units are the units in the upper right. So in this case, grams. Okay, and that is it.